Okay, dependence and independence. So a set of functions is said to be linear dependent on an interval if there exist constants that are not all zero, such that you can write a linear combinations of those functions to equal to 0 for every x on the interval. If a set of functions is not linear independent on the interval, it's said to be linear independent. Okay, so what does that mean necessarily? That means, is there a way, say we have a set of functions like this, are these functions, they can be considered independent or dependent, and on what interval? Okay, so the first question, the interval piece, is kind of, let's just think about any domain restrictions. So the only f1 and f2 have square root of x in it. So I know whatever domain I'm going to pick here, it's got to be something where I don't have negative numbers underneath the square root. So it's got to be something from 0 to infinity on that. So is there a way that we could express these functions in terms of one another where it's not all zero coefficients? If it's just a bunch of zeros, that's kind of a boring example, and that's not what we're shooting for here. So is there a way we can rewrite these things? And the answer is yes, if you're clever enough to sort of think about it there. So we can define f of 2 to be, I'm going to leave that as a mystery for just a second. So f3 of x plus f4 of x. Okay, so if I can find numbers that make those non-zeros, it's okay if some of them are zeros, but all of them cannot be zeros. So one observation I make is there's nothing to really cancel out the x squared, so that one has to be a 0 in order for it to work. But f1 and f3 seem to be able to cancel each other out. So if I take, let's just do, because we have the square root of x on one side, 5x, and is there some amount of square root of x plus 5 plus some amount of x minus 1. Some way to get that to cancel out. Well, I need 1 square root of x, so that works there, and I need the 5 to cancel out, or to match up with the 5x, and then I also need the 5 to cancel out. So if I just put a 5 there, then we're good. So, okay. So these would be considered linear dependent, and it would be dependent on that 0 to infinity. All right, I feel like this whole lesson is all about new terms and new ideas that we're eventually going to use in future lessons to develop techniques. So this is called the Wronxian. The Wronxian is a collection of partial derivatives of a series of functions. So suppose we have function f1, f2, all the way to fn, and we're able to take a bunch of derivatives. If I set up that collection into a determinant, like matrix determinant, that particular feature we refer to as the Wronxian of the function. Okay, so what does that have to do with what we just talked about? So we talked about linear dependence. In order for something to be linear independent, it has to jump through a couple property hoops. So let's let y1, y2 be a solution, be n solutions to a homogeneous differential equation of linear form. Then the set of linear independent solutions exists only if and only if the Wronxian is not equal to 0 for every x on that interval. Any set of y1, y2, all the way up to yn of n linear independent solutions of a homogeneous differential linear order different equation is said to be the fundamental set of solutions on that interval. Okay, I think this is one of those times where jumping into examples is probably going to make more sense as far as what all these definitions are. So Let's consider this differential equation. So y double minus 9y equals 0. And then we're going to let y1 be e to the 3x and y2 be e to the negative 3x. Would these be considered dependent or independent solutions? Okay, so we're going to go reach back to the dependence idea. So the dependence idea would say, is there some non-zero component that I could set y1 equal to y2? And feel free to convince yourself that that's not true. Okay, so it's got to be not dependent, simply because there is no linear combinations of those things. So linear independence means that the Wronxian has to be non-zero. So I just need to show that the Wronxian of e to the 3x and e to the negative 3x, that determinant is non-zero, and therefore they're independent solutions. So e to the 3x right here, e to the negative 3x, and then the derivative of e to the 3x is 3 e to the 3x, and the derivative here is negative 3 e to the negative 3x. Okay, so then I need to calculate the determinant of that. So that's negative 3 e to the negative 3x times e to the 3x, subtract 3 e to the 3x times e to the negative 3x. Okay, and that's negative 3 e to the negative 3x plus 3x minus 3 e to the 3x plus negative 3x, which is negative 3 e to the 0 minus 3 e to the 0, which is negative 3 minus 3, which is negative 6. Okay, so since the Wronxian is not 0, that means they are linearly independent solutions.